let me do this sort of in a reverse order. We had finished last time by saying that we are going to do an example of how this idea of Frobenius works, right? We were talking about the general regular singular point. We said Frobenius has this idea that if you take a power series and you shift it, right, you multiply it by some power, x to the r, then maybe there ought to be solutions of this form, right? And let me show you actually a little bit of how that works out before doing the example. So like how this might work out. So let's recall. So this is sort of a combination of 5.7, 5.6, regular singular points. Okay. So let's recall what happens, right? We have an equation of this form: p y double prime plus q y prime plus r y equals 0, right? And it has, say, regular singularity at x equals 0, right? And we saw that in that case, right, when you divide through by p and then multiply by x squared, right? So divide by p and multiply by x squared, you get an equation of this form: x squared y double prime plus x times some power series, right? E sub n, x to the n from 0 to infinity, y prime, plus some power series, e sub n, x to the n, y equals 0. Okay. And we said that this is why the Euler equations are the simplest form of this problem, because in that case we don't have a full-fledged power series here, but just a constant term, right? And same thing here, we just have a constant term, right? The Euler equations look like this, where these guys are replaced by just constants, right? And we said that we call something the associated or corresponding Euler equation. Okay, so given this thing, we have this thing that we call the associated Euler equation, which is just take the constant terms. So p naught x prime plus q naught y. Right. So just take the constant terms from these power series and make an Euler equation out of that. And that Euler equation has the so-called indicial equation r minus 1 plus p naught r plus q naught equals 0. So this thing which is the indicial equation form, right? And we denoted this thing by f as a form. So that's where we were, and we said that Frobenius says that, so Frobenius says something of the form x to the r summation a sub n x to the n will solve. Something like this will be a solution. Okay. And so let's see what would happen. So what would need to happen? What would need to happen for this thing to be a solution? And we just play the same games before. We differentiate, we plug this thing back into this and see what falls out. So just get y prime and y double prime, and plug in. And you end up with with this, I wouldn't really recommend writing this down, but you can if you want. You get this, n plus r, n plus r minus 1, a sub n, x to the n plus r, plus summation p sub n, x to the n from 0 to infinity, summation n from 0 to infinity, n plus r, a sub n, x to the n plus r, plus summation q sub n, x to the n from 0 to infinity, summation n from 0 to infinity, a sub n, x to the n plus r plus r. Anyway, like I said, I don't really recommend writing down. Okay, and then you basically combine terms together, and you look at the coefficients of each power, right? So let's consider the coefficients. So, for example, coefficients of x to the r, right? The lowest term is x to the r, right? When n is equal to 0, we get the x to the r term here, right? When how can we get x to the r? Only when n is 0 and n is 0 here, right? How can we get x to the r here? Only on the 0th terms of these guys, right? So you guys see, I hope, what the coefficient of x to the r must be. N would have to be 0 in the first term, right? So you get r minus 1 a naught. And then in the second term, we just take the lowest order terms in each one. So you get p naught, r a naught, right? P naught r a naught. And then the last one, same thing. We get q naught a naught. And that's the coefficient of the lowest order term. Everyone see it? We're just multiplying the polynomials, basically. You see what that is? That is a naught times r minus 1 plus p naught r plus q naught, right? Which is familiar, right? That's a naught and 1. So that's the coefficient of the x to the r term. And then for terms higher than that, coefficients of, say, x to the r plus m, if you think about it just a little bit, you see that it will be, right, how do we get, how do we get r plus m here? Well, n would have to be equal to m, right? So we just take that coefficient. We get m plus r minus 1, a sub n. Right? That's from the first guy. How do we get an r plus m here? Well, the n term here and the n term here would have to add up to m, right? So you take basically these guys as they progress from 0 to m, and these guys as they progress from in the opposite direction, like m minus. So m minus if you've got an x1 here, you want n to be m minus 1 here, so that they multiply together and get r plus m, right? You guys see what I mean? Right. So as you let these guys advance up, you want these indices to drop down, right? So that everything sums. You always get the sum m r plus m. Right? And so you get something like this, summation k from 0 to m, p n minus k, k plus r, a sub k. Yeah, right. Because that will, right. This is the coefficient. This is the coefficient on x to the m minus k, right? And this thing here, right, in here, this thing here is the coefficient on x to the k plus r, right? Coefficient of x to the k plus r in the other, right? And so when those multiply together, you see that you get x to the m minus k plus r, right? So you get something of a big power, right? And these are the only ways you can get it. So you take all these possible ways. It's just complicated. Okay, and then you get similarly for the last thing, right? You do something similar, right? You get summation q k from 0 to m again, q sub m minus k a sub k. Okay. Right. And that will again give you, those are the coefficients of powers of x that multiply to x to the r plus m. Does that make sense? I sense a deepening gloom. Yes, Kristen?
Are we going to have to?
No.
Okay. So this is a one-time,
Yes.
see this, show it, and
Yes.
then use it?
Yes.
Simpler result?
Yes. Yes.
What does that say again? Is it k?
K, that's a k. So q sub m minus k is a k.
Oh,
And this is basically an exercise in, I don't know what you call it, combinatorics or something like that. Just you know, it's basically this. You have two, you have two polynomials, a naught plus a1 x plus a n x n, and you have b1 b naught plus b1 x plus b n x n. And you're wondering what's the coefficient of like x to the r or something like that, and then you just figure it out. And it's not that important. It's important only because we needed to get this formula. So yeah, it's basically you understand what the coefficients are when you multiply two polynomials together. So let me replace these m's by n's. Just because I like n's there. Okay. So these are the coefficients. These are the coefficients of that gigantic sum, right? These are the coefficients of that gigantic sum, right? We're going to have, this coefficient. I'll call this a sub r. No, I won't. No, I really won't. We'll have this thing times x to the r, and then we'll have these guys times x to the r plus n as n varies from 1 to infinity. Right? And that sum equals 0, and so by the identity theorem, we know that each of these coefficients must be 0, just as before. Right? So, since the sum, since blah times x to the r plus summation blah x to the r plus n and infinity equals 0. Maybe I should give this some name. I'll call this capital A sub r, and I'll call this thing since this thing equaled 0, right, we wanted this thing to equal 0. We wanted it to be, when we plug that thing into the equation, to get 0, right? So, by the identity theorem again, we know that a sub r is 0, and a sub r percent is 0 for all n. All the coefficients have to be 0, because there's no other way to get the 0 function. Okay. Actually, I'm sorry, let me backtrack. I forgot to do one small thing here. Let's rewrite this thing. Let's rewrite this thing by taking off the nth term. Okay, we're going to pull the nth term out. N plus r minus 1, a sub n, plus the nth term, right? So when k is equal to n, we get p naught n plus r a sub n. And we take the nth term off this guy, that's when k is equal to n q naught a sub n. And then we have these guys, k from 0 to n minus 1. And I'm going to combine them together. I get p n minus k plus r, plus q n minus k a sub k. Okay, and then I'm actually going to write the whole thing. So what we get is that we have a naught f of r x to the r plus summation do you guys, does this look kind of familiar to you? This looks sort of like what? Like factor of the a sub n.
So what we have there.
Right, this looks like the indicial equation. This is actually f of n plus r. Right, remember f of r was this thing. Right, this thing here is f of n plus r. Everyone all right? I know it's very, very gruesome, but it will pay off. So, putting it all together, we get that we have some multiple of x to the r, and then we have some multiple things of k, r plus k, p sub n minus k, p sub n minus k plus q sub n minus k, times x to the r plus n. K goes from 0 to n minus 1, and here n goes from 1 to infinity. And this all sums to 0. So, I'm just rewriting what we have here. We figured out the coefficients, and now let's just put them back into the series. The coefficient of x to the r was this guy. The coefficient of x to the n plus r is this guy. Just wait, let's figure out the whole series. And that series has to be 0. If we want y to be the solution. If we want x to the r times summation relation a sub n x to be the solution. So we need this thing to be equal to 0. Okay. And so again, now we say by the end of the theorem, we know that each of the coefficients has to be equal to 0, right? So we know that in particular one, fr must be 0. Fr has to be 0, and further, we know this, that f of r plus n a sub n plus this thing, a sub k, r plus k, e sub n minus k plus e sub n minus k equals 0 and minus 1. The coefficient of x to the r must be 0, and the coefficient of x to the r plus n must be 0 for all n. So n, 1, 2, 3. And this basically shows you how things are going to work out. This thing is called the recurrence relation. This thing is the indicial equation, right?
What is it? What does indicial mean?
Like the indices,
Oh.
the thing that gives you the indices, the powers, R1 and R2, right? This is going to be, this is a quadratic equation. And it's going to give you, right, so the roots of the quadratic equation are called, the roots of the quadratic equation R1 and R2, they have a name, they're called exponents of the singularity. Right? And so from that, you know what the power will have to be, right? We know that we're hoping for something like this, and what we see is that R has to be a solution. R has to be a root of this polynomial, a root of this quadratic equation, right? Just like it had to be for the Euler equation. Remember, when we did the Euler equation, we got this thing, we factored it, and then we got the solutions immediately. Right? It turns out that in this case, well, we might be able to get some. We're going to need x to the r, where r is one of those roots. Okay. Exponents of singularity. So this thing is called the indicial equation. This thing is called the recurrence relation. It's called a recurrence relation because, as you see, it says that a sub n can be expressed in terms of the guise of 4. Right? Here we've got the a sub k from 0 to n minus 1. Right? So in particular, we see that a sub n is 1 over f r plus n times this thing. Q and minus k. Right. In other words, a sub n, these coefficients are all determined by the previous coefficients, and the coefficients on the power series of the analytic functions. And so this basically shows us what's going to happen when we try to do this, right? When we take a solution like this and we plug it into plug it into this sort of differential equation, we'll be forced, one, to make the power some root of the initial equation, and two, we'll see that we'll be able to calculate the coefficients in terms of the previous coefficients. Okay, there'll be some recurrence relation that gives us that allows us to, if we start off with a 0, well, a1 will be determined by a0, a2 will be determined by a1 and a0, a3 will be determined by everybody that precedes, etc., etc. Okay, and that's what's going to happen in our example once we get to it. If you guys still retain consciousness until okay. You guys see it? So this is good, right? Things look like they're going to work out, right? We will be able to determine all the coefficients, unless it turns out that. So here's the possible trouble, and this is actually real trouble. What happens if the two roots differ by an integer? If the two roots differ by an integer, and we are using the lower of the roots, then at some point, let's say that R1 is the lower root. Okay, and we're using that one. Let's take x to the R1. At some point, R1 plus n is going to equal R2, right? Because they differ by an integer, and n is going from one upwards, right? And we use the lower one. So at some point, this is going to hit R2, and we'll get f of R2. F of R2 is 0, right? Because R2 was the other root of the initial equation, right? And at that point, you lose, right? Right? How do you figure out the next coefficient? You can't, right? Because you get 0 times a sub n is something. Well, that doesn't give you any information about a sub n, right? Okay, so that's trouble. So this method basically breaks down into cases. The cases are if you have two roots and they don't differ by an integer, that's good. If you have two roots and they differ by an integer, that's bad. If you have two roots in the same, well then you need to play the trick that we played last time in place of reduction of order. Okay. So let me just say that. So observe. If R1, let's say R2 minus R1 is n naught, right? Some positive integer n naught, then we have trouble attempting to construct a solution x to the R1 summation a sub n x to the n. Right? If we take the lower root, we can't do it. But you notice we can take the higher root. Right? If we take the higher root, we're not going to run into the lower root, right? Because we're just adding on more integers. We're just adding on more positive numbers. So we're not going to run into that guy. Right? So we don't have this trouble. So in either case, if we have two guys that differ by, if the two roots differ by an integer, or if they don't differ by an integer, or if they're the same guy, we always have one solution. Right? The solution that you get by taking the larger of the roots. Does this make sense? Is anyone confused by this? It's a bit long mistake.
So I understand if you take R2, you won't run into the problem of having F.
Yeah, so we'll be able to find all the coefficients.
So you can find that solution x to the r, and that's basically telling you all of x to the r2,
yeah.
that you'll be able to find all of the coefficients.
Yeah.
But, so we still can't do x to the r1.
That's right.
Correct?
That's right.
So we just won't be able to find the coefficients of that?
That's right. That's right. In fact, there is no solution in that form.
Okay.
Okay, so
Oh,
what
okay.
in that case, we can't get a solution for that root, and you have to use a different method to get another solution.
So like in terms of like sort of the linear algebra for it, you found a solution, but you haven't found the span of solution.
That's right. You haven't found the full basis.
Right.
You found one of the elements of the basis. You can't get the other guy. So if you've got two roots that don't differ by an integer, good. You get two solutions. You've got the basis at the end, right? But if you've got a repeated root, you only get one. Or if you've got guys that differ by an integer, well, you can only take the one corresponding to the higher number. Okay, so in either of those cases, we need to find the second solution, okay, by some other method. Okay, so let's go backwards now to the example. Again, I don't know if you want to write it down, and I'm trying to type it up afterwards, so it may be better just to watch. I mean, it's up to you. Got 15 minutes. I hope that's enough. Okay. And in this example, the roots will it will turn out that the roots are don't differ by an integer, so we're in line.
Will this be the way that we're gonna have to solve like a homework problem or something?
Yes. Okay. So this is actually problem 1 from the book. 2x y prime plus y prime plus xy equals 0. This one has a singular point at x equals 0. We check to see that it's a regular singular point, right, by taking is it regular? Right, you consider 1 over 2x, multiply that guy by x. And you also consider x over 2x, that guy multiplied by x squared. Right? And you say, oh look, this is 1/2. Right? That's certainly analytic. Right? And this guy is x squared over 2. That guy is also analytic. Right? And if we wanted to, we don't really have to, but if we wanted to, we could figure out the related Euler equation by looking at the constant terms of these guys. Right? What's the constant term here? 1/2. What's so that's so the constant term of this power series, right, is 1/2. The constant term of this power series